Alright, hello everyone. So I'm going to do the introduction in English because José is from Ecuador, so Dutch is a little bit difficult, I think. So first of all, some practical info. If you have any questions during the lecture, you can just raise your hand. I will then come to you with this microphone, and when José is ready to answer your question, you can tell your question in the microphone, or you can tell it to me, and then I will ask the question. I should also note that the lecture is being recorded. For the sound, actually, the slides will be added later. So if you're uncomfortable with your voice being recorded, you can tell your question to me. Okay. Then, yeah, of course, you can also ask some questions at the end of the lecture. And what I should also say is that there are no breaks. It's, the lecture will be around 1 hour. So if you really have to go, you can go. You don't have to ask, just make a run for it. But remember to keep your face mask on when you stand up. Okay. Now our lecturer for tonight is José Oramas. I believe most of the computer science students will already know him. But just let me give a brief introduction. So José first did an engineer's degree in computer engineering in Ecuador, and then he did his PhD at KU Leuven on understanding how groups of elements from an image interact and how the relationships between them can be exploited to improve artificial visual perception problems. And this was at the Center for Processing Speech and Images at KU Leuven. And José now works at ID Lab, which is a joint lab between Antwerpen and IMEC. And he works there as an assistant professor, and his research is now about investigating exploratory and explanatory models that can identify informative intermediate representations and use them as means to justify the predictions that they make. So, without any further ado, please welcome José, and I will give the words to him.
Okay, thanks Thomas for the nice introduction. Thanks for the invitation, and WINAK for having me and for the interest on this type of topic. It's always glad to be able to speak towards motivated students. So, yeah, just to complement a little bit what Thomas already said, yes, I am part of the Internet and Data Lab. There we do a combination of connectivity and artificial intelligence, which what we call distributed intelligence. My team personally works more on fundamental topics and problems related to machine learning and artificial intelligence. My team is relatively small. The 4 persons you see there, and probably you recognize Benjamin among them, right? And besides working on those topics, I am also a very active member of the scientific community. I review articles for the journals and conferences that you see there, and also co-organize a workshop on the topics of interpretable machine learning and explainable AI. Mostly my research lies in one of these 2 groups. On your left side, you see representation learning, mostly for visual data. And that's related with my roots as a computer vision researcher in KU Leuven. More specifically, I focus on trying to explore relationships between visual elements. And this can be, for example, if you see here on the top, you see my here you see visual elements that can be features that can help you identify layouts between objects, and is the detection, that is the localization of such objects. In addition to that, we also try to look at how to exploit these elements across the temporal domain, so that we can also predict or recognize actions, things that take into account time. On your right side, what you see now is more research about model interpretation and explanation. And that will be the core of my presentation today, what is on the right side. Again, since I am mostly working on visual data, the examples that I will be giving you will be using that type of data as well. So before I go into the body of the presentation, first of all, I have to stress the fact that research is a team activity. And as such, the work that I will be presenting you is mostly a team effort involving the three persons that you see today. On the one hand, a former doctoral student, now graduated, Kylie Wang. And on the right side, Professor Tine Teutlers, which was my former mentor at KU Leuven. So, let's give some background before we start talking about the state-of-the-art research we are doing. So, as I said, my work is mostly around computer vision. And in few words, if you want to describe or define what computer vision actually is, what computer vision aims to do is really to give our computers or an algorithm, a computational system, the sense of sight that we humans possess. And by sense of sight, what I mean is the capability of understanding visual patterns, recognizing visual patterns, and also having the visual intelligence to really recognize or identify potential relationships or patterns between these more smaller visual patterns. Those are the ones that I mentioned before that can be exploited to recognize groups of objects or actions over time. But that's in theory. In practice, what it means? In practice, what it means is that if you have an input visual data, like images or video, what you would like your algorithm to do is to be capable of recognizing and localizing objects, actions, and any other activity of interest that may occur in the setting that you are interested on. Here we're looking at an urban scenario where we're interested in looking at cars, pedestrians, probably also traffic signs that might be present, and so on. Beyond localizing these objects in those bounding boxes, what we could also be interested on is recognizing actions like pedestrian crossing the streets or pedestrian walking over the zebra line. And distinguishing some of these different types of actions could actually help us to identify risky situations. For example, if a pedestrian is not crossing via the zebra line. So then the question is, how do we do that? How do we provide computer systems with that capability? One way to do this, the classical approach that was followed when I was doing my PhD, is to really try to identify or encode features, visual features, that the computer should detect, and based on those, do the recognition. So for example, if we would like to have an algorithm that could recognize bikes, what we could do is tell the machine to look for round edges, which could be used to describe the wheels. And similarly, for other more straight edges that could be used to recognize the quadrant of the bike. The same can be done with colors and so on. So what you see here actually is a more advanced version of that, which is the Deformable Parts Model, or DPMs, proposed by Felsenswolf et al. In 2010. And what that method did was that based on these low-level features that you see represented in the bottom, it learned how to group them, and you see the result in the blue boxes, so that it can recognize parts that frequently occur in the objects that they were interested, bikes in this example, so that they, when composed together, could recognize bikes or cars and so on. Yeah. Once this, let's say, feature engineering was defined from data, then the goal was, the next step was to push all these features, all the data translated into features, was then pushed into a machine learning method, which could be an SVM, could be a random forest, decision tree, pick the ones you like the most. And then it was the task of the machine learning method to really figure out how to make decisions from these features that an engineer, a scientist, handcrafted in order to help the recognition task. So this feature extraction include the design of this interest points detector which required some engineering. There was someone who needed to analyze the problem and indicate what were important features that could be indicated. And this was more or less the common process that was followed until 2012. But what happened in 2012? Well, what happened was what we see there. This is actually the performance plot on your vertical axis, the top 5 error, on the recognition in the ImageNet large-scale classification challenge. And that challenge, actually, what it entails is 1 million images, which composes 1,000 categories, object categories. And the idea was that the machine needed, or the algorithm needed to be able to recognize, given an image, which of the 1,000 categories was present. Given the large volume of data and the large amount of classes, categories to be recognized, this was a very complex problem. And what we see in that circle in 2012 was the performance achieved by AlexNet, which was one of the first deep models that was very successful at this task. And something to notice is the significant margin in performance with respect to the winner of the previous year in 2011, which is actually more than 10 percentage points of error. Yeah. And from then on, all the methods that follow, the winners of the following years, were nothing more than methods based on deep architectures. After this was observed, larger companies like Facebook, Google, who had research teams, started to look into these type of models and started to figure out ways to integrate these things in their models. And the way these models are trained are actually following this paradigm, where what we have is a large data set with images or examples of the class of interest. Could be text, if what we are doing is text classification. And for the case of supervised learning, for each image, we also have a label. In this example, each of those images may have the type of cat that we are visualizing there. Then the idea is to push all these examples paired with labels through a large and deep neural network. And at the end, eventually after training, this model will learn to identify a specific characteristic on the input data that will help make the prediction as good as possible. In doing so, this engineering that was required to tell the model the features that are important was not necessary anymore, because now we have this complex interconnected model which is in charge of learning that automatically. And the main idea was just let the model figure it out, what are these features. Humans do not need to indicate that by hand. And this is what is known as representation learning, formally speaking, or more popular speaking, deep learning. Yeah? And as I said before, given the high performance of these models, many more companies started to adopt them, and we started to see in the news some success cases on the application of these models, where in some cases they really achieve a state-of-the-art performance, and in very specific tasks, they manage to overperform humans themselves. Also, given the high adoption of these models, the PyTorch and TensorFlow frameworks were developed with the goal of easing the development of algorithms that are based on these type of models. And so came we to this type of architectures that is composed by a sequence of layers where the input goes from one side to the other and follows a large set of small operations internally. But what is the main problem? The main problem is that these models are so deep and so interconnected that it's relatively complicated to tell what the model has actually learned internally, because there is just so much information inside. This problem is usually called interpretation. The other problem that we are facing is that when the model makes a prediction, for example, tiger cat, for this image, it is really hard to tell, to justify why the model is actually telling you that that image is of a tiger cat. It's hard to justify the prediction. And that's what we call explanation. So the question is, if these deep neural networks have high performance, why are we interested in having these two interpretation and explanation capabilities? Well, on the one hand, it's because these models are not really perfect, and they really depend on the data they are trained on. And here's an example where 3 commercial face detectors from 3 different companies were tested on people from different races and genders. And what was observed is that depending on the gender and the skin color combination, a significant margin in performance was obtained. So what was observed was if we had a lighter male, for example, in some cases we obtained near 100% performance, whereas if we had a female with dark skin, we got something around 65 performance, which is quite a huge margin for these 2 different persons. And it's more critical since this is really making decisions about people. Another example that I am showing here is in this super resolution task, where the idea is that given a small image, we would like to make one that is more detailed. Yeah? And the result looks quite nice, quite good. However, we can see that it's quite bad if we consider the real image where that low resolution image came from. So we can see that there is also some bias injected in there, more towards light-skinned people and those apparently with lighter hair color. So in some cases, either the bias can come from the data or from the model itself, like in the right side. Another motivation for having these things is that the features that humans use to solve a problem are not necessarily the same as those that these models identify. So by figuring out what the model is actually doing, we can verify whether there is new information that can be exploited to solve a specific problem. And this was the case for the use setting of weather forecasting. Yeah. And maybe finally, what is also very important is because there are 2 popular roles that AI normally has. And knowing what the models are doing internally can help you clarify these 2 roles. On the one hand, probably, you have heard that AI is nothing more than a nice magic box that can solve any problem you throw at it. Yeah? The other popular role, personally more favorite movie of myself, is that one of being the doom of mankind. That AI is so smart that it will outsmart humans and enslave us. Right? By knowing what goes on internally and how they operate, then it's easier really to know what are the limitations and what the really capabilities are. Therefore, you can have a more critical view on this type of algorithms and machine learning models. And you will be able to really have a critical argument with someone trying to sell you any of these 2 ideas. So now let's discuss what we have done around the task of model interpretation and explanation. But maybe more practically speaking, let's try to clarify why do I really mean when I say model interpretation or model explanation in a computer vision context. So let's start with explanation, which is, I think, the easiest of the 2 to explain. So the idea is really trying to justify the prediction of the model. So if I give the input, as input to my model, this nice image of, what are those, lioness? Something like a female lion. And I get as output that my model says that's the image of a female lion, I would like to have some indication of what were the parts of the input that justify, that support that prediction. In this case, a common way to generate that supporting information is by producing these heat maps that give, in this case, a reddish color to pixels, the parts of the input that have a stronger influence in the decision. I don't know if it's clear from your side, but that heat map is overlaid on top of that input image. So to a good extent, the overlap seems to be on the faces of the three lines. No. In the case of interpretation, the idea is to provide insight of what features are internally encoded by the model. In practice, there are several ways to do this. There is not a standardized ways, as is the case for explanation, where they normally use heat maps. In the case of visual data, a common practice is to try to measure the overlap of the different activations that the input has inside the model with a set of annotated images, where each image indicates where specific objects are located, like here's a car, here's a person, and so on. And by measuring the overlap with what happens internally in the model, you can produce a histogram that tells you which specific object categories your model encodes internally. In our case, we will try to do it via visualizations of those features that are internally encoded. So how do we do interpretation in my team? So given that we have a pre-trained model, that model has already been trained in advance, we will look at all the classes that it has been trained to recognize. And for each of those classes, we will identify what are the most relevant features that the model knows about them. So for example, if it knows how to recognize a bird, I want to know for the specific bird category, what are the characteristics, the visual characteristics that the model is using to make decisions. And then for each of those characteristics, we will make a small visualization. And that's what will help us recognize, identify what are those features. So how we will do that? So we will push every image through the model, and the image will follow some path, like represented here in blue, until making a prediction. And the way we will identify these relevant features is via this optimization that you see here, where X is all the internal activations that the input follows when it's pushed inside the model. L is the actual prediction that the model makes. And the idea is that we want to identify relationships between these two, between the activations inside the model and the prediction. And we do that by learning this set of weights, which will give a weight to every internal activation, And that means that higher weights will represent more relevance, more importance towards the prediction. However, something that is important is that because these models are so dense and so deep, this flow of activations, this vector X, can be in the orders of the hundreds of thousands dimensions or even millions. Yeah, and that's quite a large vector, especially if we want to make visualizations of each of those features for the person trying to interpret the model. That's too much information. So we will focus the features that we will be visualizing. And for that, we impose some sparsity parameters, some sparsity constraint, so that we will only look at the most important, the ones that have the strongest role on saying that this image is a tiger cat. Yeah? And we do that with this constraint that you see here, which is represented by the sparse dots. As a result, for each class, I will have a subset of features that I know are very important inside the model to recognize the class. What that also means is that for each of those features, I will know on which layer, which of these blocks that you see there, the feature is located, and also on which filter produces that feature. And in this case, if you're not familiar with what the filters are, you have to see them as one of the slices inside each of these blocks. So those will be the coordinates that I will obtain once detecting which are the most relevant features. And once I know where they are, for example, for the case of cat, I can visualize, I can show the activation map of that specific slice, that is where the red point is located here. I will just take the slides there and get that slide there. And then I will look for the highest activation point. In this case, that activation point seems to be around the nose of the cat. And using the parameters of the architecture, I can know that in that specific channel or filter of that layer, the neuron that produces that activation has that coverage, which you see in the red square. Then I can consider that area in the input that produces that activation. Yeah? And repeating this process for all the images of this class, in this case the cat, I will take all those small regions that you see in the middle, and I can do an average image. And I will come to something like this, where what you see on the right side is actually a visualization of how the feature that is so important looks like. And in this case, we see that it really looks like the nose and part of the mouth of the cat. So that's one of the features that is important for that specific type of cat. And we have repeated the same process for all the 1,000 classes. There you see a subset, where for each class, we are showing some examples of some of these features. In some cases, it's more evident than other what the underlying feature actually represents. So for example, if we look at the robin case in the end, we see that we have a close-up to the head of the bird and other images that are a bit more of zoom out. And the same we can see, for example, with the balloon, where we see different parts of the balloon, or here focusing more on the basket. So the idea is that to get a notion of what are these characteristics. Of course, depending on the data set, these visualizations will be more or less clear. Yeah. So once we have done the explanation, the interpretation, we will justify the model, the predictions made by this model in the following way. We will first push the inputs through the model, in this case, these two images, and obtain the predictions that the model makes. Then for each of those classes, tiger and tiger cat, we will look for the features that are from the most relevant from tiger and cat that were identified in the previous step, and do visualizations of the top 3 features with the highest activations. And that will give us this result here, where we see that for the tiger, some features around the eyes, the mustache, and the nose seem to be important. Whereas for the cat, strangely enough, we see that the background has a strong relevance. And looking at the data, at images of this specific class, we realize that this type of cat is a home cat, is a domestic cat. And a lot of the images in the dataset that belong to this class were actually taken in parks and indoors. So indoors in the backyard of people's houses. So in most of the cases, grass was present, and therefore the model learned to pick up this feature. So to some extent, it is really modeling that is the context on which this specific class occurs, what matters. Yeah. So this is how we do what my team has developed regarding object interpretation and explanation. But the question and the main goal of this talk is actually to show what can be gained by knowing these things. And the first case that I will show you is the one of object localization. And more specifically, how we can reduce the level of required annotated data in order to do object localization. So before we go to localization, let's talk about detection. And what detection is providing some cues, some indicator of where my object of interest is actually located in the image. In this case, that extra information is in the form of this bounding box that you see here in blue. And normally that's indicated via the coordinates x1 and y1, and w and h that you see here, these 4 parameters. What that also means is that if you want to train an object detector, you need to provide, on the one hand, the data, which are the images, and 5 specific labels. One that indicates the category, which is car, and the other 4 that are related with the bounding box where the car is located. And what is the main issue with this? The main issue is that if you want to have, let's assume, a general object detector which can recognize any object, you will need to provide, someone will have to manually get all these extra labels regarding the location.
And what I will show you is that by exploiting the internals of the model, we will be able to do detection without getting that additional information. We will only use the category information. So the assumption is that we have a classifier that can tell me, in that image, there is a car. I don't know where, but I know there is a car. Yeah? So we assume that model exists. And that type of problem is what we call localization, object localization. We know there is a car, but we don't know where. And how this has been solved so far? This has been addressed in the following manner, by the so-called class activation mapping technique, where the idea is that if we have a model, we will replace the last convolutional layers with one layer that will learn how to apply weights to the last 2D feature maps that model has. And in doing so, it can apply later those weights and do a linear combination of with each of those feature maps. That is what you see here, these three. So these three actually come from this layer here. Yeah? And in doing so, the model can provide an explanation of what is the region that justify the prediction. In this case, the class was Australian Terrier, which is located here, and the resulting explanation is highlighting this part. So what we want to exploit is actually all these internal cues in order to help localizing perfectly the object. And why I stress the perfectly part is because there are some problems with this technique. And as you can see there, in red, in each of those images, the bounding box in red that has been predicted by the model is not 100% optimal. And as you can see, it's much smaller than the expected bounding box, which is in green. That's what we call underestimation. Similarly, we have the other type of problem, where now my bounding box, the predicted one in red, is much larger than the one that is expected. And that is because as we can notice, the heat map that is under it, or that is used to estimate it, to estimate the red bounding box, is a bit coarse, it's too smooth, and it stretches too much over the image. And therefore, the bounding box that we estimate is much larger. Yeah. So what has been done to try to address this issue? On the one hand, for the underestimation, if we have an image like that one, what is done is that we drop, once we know that this is important, we just drop it. We just occlude it in the input when we train the model. And what we force the model to do is to look for other characteristics that are also important. For example, if we are talking about birds, we are telling, okay, I realize you noted that the body of the bird is important. And by removing it, we expect that the model will start paying attention to the wings. And as a result, my heat map will spread a little bit towards the wings. And as a consequence, my bounding box will also extend, because the bounding box comes from the heat map. The other solution that has been put forward is to compute the class activation mapping for all the classes that the model can predict. Not just birds, but all of them. And the idea is that once I have information from all of them, the heat maps from all of them, I can write a combination function that will try to remove features that are shared. And in doing so, my heat map will be able to concentrate more on what defines a bird in this case. Yeah? But both techniques have their problems on their own. The first, that is straightforward, is that they are specific for one of the two problems. In this case, what we are proposing is to have something that can address the two. And what we do is we will start again from the same CAM-based method, but we will add an additional branch, which will focus on improving localization. Not just prediction, classification, but also localization. And what is more important is that we will only update this part of the network. And what that means is that once we are done with the training, we can go back to the original model, and this part of the network will be optimized to do both classification and localization, and we get an object detector as a result, without using location-specific data. And how we do that? So for the overestimation problem, let's assume that we have those 5 images, and that these red boxes that you see around are the bounding boxes that have been estimated from a heat map that was calculated. Yeah? Just for the sake of clarity, I'm not showing the heat map, but assume that the heat map extends as much as the red boxes that you see there. Yeah? What we are assuming in our solution is that if we have images of the same category, in this case that type of bird, they should all have the same representation. We are imposing that constraint. And what that means is, for example, and how we compute that representation. What we have here, I is my input image, H is the heat map, that in this case is just represented by the red box. And the idea is that once we have the heat map, we will do a pixel-wise product, which will remove some regions of the input. And B is actually the representation that is obtained after pushing it through the model. So if we do that for every of these 5 images, we will force that the result is similar for the 5 of them, because they all represent the same object, in this case that bird. And that's what you see in this equation here, actually, where we measure the differences between the two, between 2 of these images. So we try all the pairs of images, and then we have this normalization term, which considers the number of images in my set. In this case, 5. Yeah, and because we're enforcing this common characteristic, we call this common region regularization. We do something a bit different for the case of underestimation. And here the idea is that if my image is supposed to be of a given class category, object category, the representation of that image, of the full image, should be similar to the representation that the heat map of the given category highlights. Yeah? So if this is the representation of, if this image belongs to a bird, that means that the heat map of the whole image should be as similar as possible to the heat map of class bird. And that will have the result that that red box will be a bit stretched. And again, we do that for groups of images, in this case S, and we measure the difference between the representation inside the little box and outside and the complete image. We test that in different data sets and with different model architectures. And here you see some results of what happened, how it was before and after we applied our method. So as you can see, in both underestimation and overestimation, now the red box gets closer to what is expected if we consider the green box. It's not perfect, but it's much better than what we had before we applied our method. Okay? Here we have more examples, not just with animals, but also with some man-made objects on the right side. And the trend is more or less similar. We tested this in a more quantitative manner, where we measure how much was this overlap between the 2 boxes that I'm always showing. In each row in this table, you see a different architecture, like BGG, ResNet, MobileNet. And what these architectures are nothing more than different compositions of these models, different number of layers and so on. And each of these 3 different columns, what you see is a different data set. Some of them are bird images. There is also the famous ImageNet, which has 1,000 categories, and Open Images, which is a more diverse data set. On the first row of each of these 3 groups, you see the performance of CAM, which is the basic method that I explained before. Then what you see is a set of methods which were the ones that came after CAM. Yeah? For CAM, for CAM, we show the absolute performance in different metrics. And for the rest of the methods, we show what is the relative performance, the difference. So for example, here we indicate that this method is 0.7 percentage points better than this one here. And this is the opposite. This is lower because it's a negative value. And what we can see is that in general, our method has the highest improvement over the three architectures and over the 3 data sets. So it's always better. We also analyze what is the effect of the set size, how many images we consider. And what you see in the bottom again is CAM, the basic CAM. And here when it's the case when the set is equal to 2. So when we use our method and we only use 2 images, we already see a notable improvement of around 8%, 8 percentage points. And it keeps increasing as we go higher. In our experiments, we mostly focus on sets of size 5. But we wanted to do this experiment just to verify what is the effect. Now, this is another result. I will not bother you too much with the details here, but the idea is that we have these 2 components, common region regularization and full region regularization, which the 2 address the problems I showed you before. And the idea is that when we train our model, we need to find a good trade-off between these 2. What you see here is more or less what will happen if we weight differently these 2 components. And what I want to illustrate here is that the flexibility that the method has to address different architectures. Because the problems I stated of overestimation and underestimation are actually more prevalent in some specific architectures than in others. So by weighting our method properly, you can actually address both problems in any of the architectures that you may encounter them. And the question is, okay, the visualizations look nice, the numbers were also interesting, but is it perfect? And the question is, of course not. The answer is, of course not. There are 2 types of failures that we have identified when analyzing our results. The first one you see on top, where we can see this duck on a pond and the reflection is also considered in our heat map, therefore also in our bounding box. And that really shows you that these models, some of these models, in particular the ones we're working here, are nothing more than pattern recognition methods, right? They have realized that the features that are in the water, in the water, look very similar to the ones that are above. And the ones that are above are actually important to recognize ducks. That's why it has highlighted them. In this case, the model is silly enough to not realize that these features that are in the bottom are nothing more than a reflection. And that's why it's highlighting them. And it's causing an error in the estimation. In the second case, the type 2 failure, what you see is that our heat map and bounding box is also taking into account the branch of the tree where the bird is always standing. And what we notice is that indeed, for some of the bird categories, the images always show the bird plus the part of a tree, or water like with the duck. And in this case, because this context was always present, the model was not smart enough to realize that this part that I'm always seeing here with the bird is not part of the bird. Yes? So that's to show you that even though they are good, these models are still silly. Let's go to another problem. And this one is related with the image that I showed you before, doing super resolution. And I will show you that here we can both get insights in the problem and also enable additional capabilities. And by that I mean addressing other problems. So let's first define the problem. So super resolution means going from a low resolution, very pixelated input to something that is more detailed and larger in scale. Something to point out here is the specific setting that I am showing here, where the input has such a low resolution that even for humans, it's very hard to realize, to imagine how the eyes, the nose, how the details should look like. Yeah? And that's why under this scenario where the jump is too large, this problem is usually called image hallucination, because the machine needs to really hallucinate how this pixelated input should look when rendered in a detailed manner. And the way we solve this problem is by in addition to the input, provide a set of high-resolution exemplars. In our case, the exemplars are nothing more than other images of the person that is under the pixelated image, but these exemplars are in high resolution. So the idea is that these exemplars will help the model get the information related to how to fill in the details that should be presented in the output. Yeah? So we start from a standard convolutional neural network, which does deconvolutions and tries to expand every pixel in the input a bit further. Of course, there is also a discriminator at the end that tries to assess the quality of the resulting output. I will not go much into details into that, since it's a standard component. But what I will describe more in detail is the component that we added, which is this branch. And what this branch does, it takes a set of inputs, high resolution, related to the low resolution image that I want to upscale. And by processing, we will push them into what we call the PW module, and it will inject features from these inputs to different parts of the process. Yeah? And in doing so, it will really help the original model to figure out how to fill in details related to eyes, related to nose, lips, so on and so forth. So let's see how that works more or less. So we have here 3 inputs. Here what you see are 3 exemplars, like the exemplars that were provided to each of those inputs. What you also see is actually the weights that this module gave to each of those exemplars. Again, red value means high importance. Blue value means low importance. And that's interesting to see, for example, in the case of the persons with glasses. In both cases, the input, even though it's pixelated, it doesn't look to be using glasses. And the model seems to have realized it. And therefore, on the regions related to glasses, the weights are dark blue, which means low. They are not that important. Yeah. This is what we get as a result after we do a super resolution process. And the results are relatively good if you compare them with what is expected on the original image. Yeah, so the super resolution process is quite decent. Something to notice is, of course, that it's not exactly the same. In some cases, you will notice that maybe the eyes of the man are not exactly the same with the woman here, and I think also the eyes of the woman are not necessarily here the same. No? So there is small variations. Even though the image is not pixelated anymore and has more details, it's not 100% as similar as what we would expect from the original. Yeah? So far I have shown you that it is interesting. We have gotten some insights on how my model works internally. And overall, what we have seen is that every time we give a pixelated input, some exemplars, and we get some nice high-res output. But then one of the questions my student made back then was, what will happen if suddenly we give a different set of exemplars, right? Before it was always exemplars from the same identity, the same person. But what if we change those? And what we got were actually these specific images where some facial attributes were now modified. Now the guy doesn't have a light beard anymore. Now the skin seems to be a bit more smoother towards the chin. Also the eyes seem to have a little bit of makeup. Yeah? So we realized that by modifying these exemplars, we could actually edit a bit the facial features of the result. And this is interesting because back then, the only way to do this facial modification was by already burning in the model the set of attributes that I would be capable of modifying, right? And later, at this time, I could just say, I want to modify this. The problem is that if there is an attribute that is not supported, I will not be able to modify it. In this setting, we have made it a little bit more flexible. And that is, depending on the input you provide, that input should have the attribute you want to inject. And that way, you have the flexibility of adding anything you want. Yeah. Make it, and now finally moving something to more recent, still experimental and ongoing, is the task of making visual explanations, that is these heat maps, in such a manner that they are more accessible for us humans. And this comes from the observation from Adebayo et al. Long ago, that realized that some of these heat maps that are generated as explanations are not necessarily justifying the model they are trying to explain. In some cases, they were really biased towards characteristics of the input, like, for example, regions with strong gradients, like these edges that you see around the neck here, where there is a large difference between color, or maybe the prediction, the label. So it didn't matter what the input image was, or what the model is doing internally. This heat map was independent of such steps. Then we did a follow-up analysis, and the question we analyzed was, let's check whether these heat maps, at least the ones that are known to be good and robust to these issues, could be used as tools to identify deep fakes. And as such, we fed the machine, we trained a model that was capable of predicting yes or no, fake or real. And we fed it an image like this one, that we knew was fake. Yeah, we generated it, we made this deep fake, and we push it through the model. We got the fake class, the fake prediction, which was correct, and then use an explanation algorithm. When we use the explanation algorithm, we got something like this on the right side. And then it's a little bit hard to tell exactly why my model thinks that that image is fake if I only pay attention to what I see on the right. Here on the left, I have highlighted some part that is quite noticeable, that shows you that that image is not natural, that has been manipulated somehow. But according to the model, there are also things around the eyes and the nose, and in a lot of other places. Yeah. And then the question is why? Why exactly the model is trying to tell us? And we then started to look even deeper on what was going on. What were the features inside the model that were leading to these visualizations? And by doing a deeper analysis, we came to the realization that features that the model uses are not necessarily the same features that we humans use. Yeah? So that's something that was already a little bit known. Yeah. But what was not known is that some of these features were not perceptible by humans. Yeah? And to give an example, in some of these images that were generated, the generation process was introducing some kind of texture. So parts of the skin or the background were not flat, but they had small variations, very small pixel variations. Variations that we humans could not perceive. Yeah? And that's why in some of these heat maps, we see, like, for example, here on the back, this green region here above, or on the faces, or, yeah? Because we cannot notice something there, but there is a small variation that the algorithm is very good at picking. Yeah? And we realized that this pattern, this high frequency noise, was injected as part of the deepfake generation process. So the way the issue with that is that it doesn't matter how good your explanation method is. If the features themselves are not perceptible, there's no way we humans will be able to understand what the explanation is telling me. So what we did was to filter or preprocess the inputs so that by looking at human perception models and so on, so that whatever goes into the model will be able to be perceived by humans. And in doing so, we managed to get this, after doing that cleaning of the inputs, we managed to get this type of explanation that is the one you see on the right side, where the model is focusing a little bit, the explanation is focusing a little bit more on indeed, the problems, the more noticeable problems, to call it in one way. Here are other examples that I can show you related to that. And something that we also notice is that these issues are not necessarily on the people faces, but also in the background, because the deepfakes actually generate the complete image. So sometimes those issues are related with things that occur in the background. Like if there is text, when the text is generated, it's not 100% properly generated, and the model highlights it. Yeah, again, this is very experimental. This is still in early phase, and here's a preprint with more details. So to conclude, I hope that with this talk, it is clear for you that deep neural networks are not as opaque or black boxes as it was initially stated back in 2012. There are several methods to interpret and help explain the predictions of this model. However, they are not that perfect, as I tried to state in the last part. Understanding the inner workings of these models can bring some advantages. For example, first of all, we will get transparency on what's going on. And that's very required nowadays based on GDPR. If you are developing a platform, a system that makes predictions about people, the people have the right of explanation. So you will have to embed this type of mechanisms. As also show you that by understanding how they work, you can reduce the annotation requirements, like we did with object localization, and also improve and enable new tasks, like I showed you with facial edition. And maybe finally, that AI-related technologies have improved a lot in the last decade, but they are far from being perfect. And that's why, for you and for us, as developers, researchers, designers of these algorithms, it's important to do sanity checks, to develop do interpretation and explanations on these methods, just to make sure that this is properly tested before it goes out in the wild and is deployed into production. Thanks for your attention. And if you would like more details about that, in this QR code is the link to my website. So there are all the papers and other more than the ones that I presented here. Thank you.
Right, thank you, José. Are there any questions? Yeah, Jeff?
I had a question about the last part. So you developed this method to make sure that this model only focuses on properties that are also visible to humans, but why should this be desirable exactly? If we know that the machine is looking at certain things that only the machine can understand, but we do know that it's looking at those properties, why should we restrict it to things that only humans can see?
No, yeah, that's a very good question indeed. So there are two, let's say, directions or angles that we have to take in mind for this part. On the first one, if we're talking about a safety point of view, let's say an autonomous driving platform, and I want to use these explanation algorithms as a way to debug my model before I put it in the car and sell it. Indeed, really using all the features that are available for my model is the way to go. And that's important if you have a researcher or an engineer behind, let's say, looking at the explanations, because they might be the people capable of understanding what's going on. Yeah? But on the other hand, we also have models that are interfacing regular people, end users, that have no idea about, let's say, computer science or high frequencies, which is even more complex. Yeah? So for those, we need to some extent, accommodate the output, the feedback, so it's understandable for them. Yeah? And that's more or less where this last part goes, to really provide the means to be able to address different types of users. Of course, this part of the different types of users is usually coupled with research on human-computer interaction and people understanding human factors. to be able to address the needs of the user properly. So yeah, this goes more towards this work that is not really 100% objective, but tries to take into account also the human side, the person feeding from the explanations. Yes, very good question. Thank you.
Right. Are there any other questions? No?
Yeah. I have one question about the exemplars in the super resolution process.
Mm-hmm.
How do you pick these exemplars for the pictures?
Yeah. In this case, our data set for this is a data set of celebrity, and for each celebrity there is a set of images. So what we did was, for every image, we randomly selected 3 or 5 or a set of exemplars from the rest. Here, the only requirement, at least for the basic super resolution step, is that they should be they should have the same identity. Yeah, but that, at least for the sake of this study, that's how we did it. Yes. Yeah, and something that you should maybe, if you pay more attention to this, is that we just don't feed the exemplars directly, but there is some type of alignment process prior to that, where if you can see most of the pictures, even though in some cases there is a little bit of an angle, like the eyes, nose, they are trying to be a little bit aligned. So to make it a little bit easier for the machine to figure out what to pick from where. Yes, but that's how we did it. Thank you.
So on one of the next slides with is this one. So when we add the photos of persons that don't match so like the moments over here, when you also add the photos of the men, do you still get a photo of the man? So a result of a man, or do the woman parts get mixed in? Because the model should know that the moments don't match.
Well, so if I understand correctly, so what you mean is if I mix the exemplars, if I have man and woman there together, is that what you mean?
Yes.
So that experiment really we didn't try. So I cannot answer that one. We just, as I told you, we just, to Joshua, we only look at another identity. In this case was the identity of this woman, which is the same, and just fed exemplars from that image, from that woman. We sampled exemplars from that woman. But that's a very good question, actually. What would happen if suddenly we mix the exemplars? What I will guess is that we will get also like a kind of mixed result there in the end. Like, for example, we may get, let's say the lips will be a composition of what the exemplars are. So that's actually what you see here is also happening. In this case, the features are a bit female-ish because, or girlish, because all of the exemplars are the same lady. Yeah? And and the composition of them leads to something that is more woman-like. But if we mix them, yeah, then it will be a composition, but I don't know how it will look, to be honest, because we have not tried. But it's a very nice experiment to do, indeed.
Okay, thank you.
A while back in the presentation, there was this idea that you look at the heat map of what a certain layer of a neural model does, and so we looked at it and we saw that the model of the cat was specifically like looking at the nose of the cat. This might be looking too much of it as a regular machine, but is there some consistency to what a specific layer does? Like if we input another image of a cat that's maybe looking in the same direction or looking sideways, will that layer always be the nose layer that looks at the nose, or will it be very varied?
No, that's a good question. So the idea, what you're asking is whether there is a specific semantic concept that is picked up or that is modeled by a given layer in the network. Yes, and to some extent, I wouldn't say it's a semantic concept, but a specific visual pattern. In this case, for example, going back, maybe that's more related with this visualization. Yeah? In this case, on the right side, it is clear that the visual pattern that we see there is related with the nose of the cat, or with the trunk of the cat. Yeah? And we can say that because we see it and we recognize, okay, that looks like a trunk of a cat. Yeah, the machine doesn't know that. What will happen if we bring another image of another cat? Yeah? It will really depend. because each of these different layers and the filters inside the layers pick up different characteristics. For example, if in this case the filter picks both color and shape, yeah, we see what is the result there. If we input the image of a puma or a cougar, yeah, the colors are more or less similar, yeah, and the shape as well. So it is likely that with that class, we will also get a high response with that specific feature, yes. But let's assume for a moment that my feature ignores color. It only pays attention to the shape. Or no, sorry, let's stay with color. And now I give the image of a Panthera. Panthera, is that the right? Yeah. The black one. Yeah? That will look completely different to this. A panther. That will look completely different to this. And that will not activate. When the image reaches that location, it will not activate because it looks different. These filters only give a high value when they are overlapped to a region that looks exactly like what they encode. In this case, something like that. Yeah, and the idea is that it's not a problem that they are shared, because that's actually one of the strengths of this type of models, that they learn features that can be also shared between different classes. And as you go deep in the model, for example, yeah, well, like this, sorry. Yeah, the idea is that in the first layers, you learn very low-level features, like edges, colors. In the next one, you learn how to group them, like to form wheels, parts of objects. And then later, objects themselves, and maybe scenes. So it's always a composition. And in some cases, this can be reused for other classes, other concepts. Yeah, so that's per se not a problem if they are shared. Yes. And we notice that when we look for the relevant features, that in some cases, they were shared between different similar classes, like in this case, breeds of cats. Yeah?
Any other questions? No. Okay, thank you very much for the questions, and thanks again, José, to you for the interesting lecture. The lecture, as I said at the beginning, will be uploaded on YouTube. So you can also look again at the slides, and thank you all for coming. So, and maybe till the next time.
Thank you.